basically sold the actual ending of the game as DLC.
Yeah, it's
Thank
like
you, Capcom.
Yeah, you literally could not get the ending of the game unless you bought the DLC or something.
I remember that from a service wrath.
I like what Hollow Knight.
What have you done to us, Oblivion's horse armor? What have you done to us?
Don't worry. 20 years later, and he got me again.
Right?
And admittedly, he gave more free armors and the actual soundtrack with it as well. So, okay, it's not just the horse armor this time, Todd.
I could say something real quick too. It's like we went from horse armor to, I play a game called SMT Nocturne. We went from horse armor to now I have to pay money to get an easier mode.
Right.
So like, oh yeah, this game's too hard. I need to put down $10 so I can get an even babier mode for this game.
I have the original Nocturne on the PlayStation 2 that came with the original soundtrack on a separate disc.
Oh wow.
Yeah, that was a rare game back in the day.
So glad Hollow Knight, $15 game, already an 80-hour game. They released years of DLC for free afterwards as well.
Yeah, that's my view on Path of Exile. I've gotten 10,000 hours out of that. And I am on to it. I started a game last night with an hour of time that I had, and I'm vastly intrigued by it. So we'll see how it goes. But it was just released, it went out of early access 3 days ago, right when I bought it yesterday. It's the Slormancer. I am an action RPG nut, but it has a very interesting progression system that I am very interested in. So let's actually talk about some compilers. Games are fun and all. That's my other class.
Oh, let's just show up at 2 o'clock Monday and Wednesday in that room.
Exactly.
We're gonna go.
So we went through, again, the code optimization process, kind of the mapping of lines of program into converting them into more assembly-like instructions. Let's actually just go back through those. We've already seen this a couple times, but turning any expressions into something that maps easier into assembly type instructions, where now we're using at most 3 variables, meaning at most 3 registers in any of our expressions, since we can't utilize more than 3 registers in any assembly call. We then go into the code optimizer that looks for, is there any way to remove any of these variables to make this a little bit more efficient? We talked about how it's very important to make sure that you're not losing any information or making any assumptions when you do this, because the user has no input or is not necessarily even aware that this is going on. So anything that you do at this stage must just be a strict optimization. Then we end up with some assembly generation or machine code generation or something that is the target language that is much lower level than what we started with. But based on those changes, we now have a much easier mapping between the intermediate code generation, which is in the language that you wrote it in, and some kind of assembly instructions. So temp1 equals A plus B now directly maps to 4 assembly instructions. Last thing we want to cover here is what else is needed. What are the structures that a compiler needs to interface with and use in order to do these? So the first one is a symbol table. This is just a table that stores information about the identifiers that it runs across over the course of the program. Any variable names that you're going to refer to later, we need some way, some map of being able to look up, when I refer to the variable C, look up what its value is. Any function name, if I call a function, we need to know what are the set of instructions that are mapped to that function name. So as we parse this, we're going to start to store these identifiers and where to begin looking at that information in this table. So as we scan, we recognize the identifiers, we add them to the symbol table. We, of course, have to check that they're not already there. You don't want to create duplicate entries, but if you make it and treat it like a set, then you won't have that issue. Parsing will add information to the table as soon as we learn an associated variable type for it, when we're able to validate that, all right, it's declared as this particular type. If we know that it's this particular type, then we can add that to the table. Type checking will refer to the table to make sure that the declared type is the same as the evaluated type, or something that can be cast for free without a user-defined type, without a user-defined cast. So that's everything in the symbol table. We populate it at the beginning, and then we start to refer to it to be able to map things in the type checking stage of the process, the semantics checking. We also do some error checking. So when we're scanning, we may have a token that doesn't match a token type that we're expecting. Maybe it's an illegal variable name. Maybe there's something that we're doing there that if the compiler is going to fail to compile this program, how do we recognize what happened, where it happened, and generate some kind of error that we can return to the user? In parsing, we may have some group of tokens that don't match some production that we're expecting. So there's a syntax error in the program, and we need to tell the user that there is a syntax error. We need to figure out, to the best of our understanding, what happened, where it was in their original program, so that we can report that back to them. Anytime that you see something like syntax error on this line, that is the error checking algorithm within the compiler that is determining that at one of these steps. If you get a cannot convert between int and string, something like this, then obviously that happened at the semantics stage of the compilation process. So the next time you're writing something and you get compilation errors, my recommendation to you is to think about what stage in the compilation process defined that. Also, fun thing I noticed yesterday on my way home, there is a book out of the free, there are 4 books left. One of the books that no one has taken to this point is an older book, but it's writing a compiler for C or something like this. It's a massive book, and no one has had any interest in taking that book home or reading it. I just find that kind of funny and thought I could share it in this class. If any of you want to go look at that, I think that would be really interesting, but no one else in this degree is going to be able to appreciate that book at quite the level now that I think all of you will, having been through this class. So you want a free old book on compiling C? There you go. It's on that bookshelf or the cart out there.
Oh, is that floor 3?
It's right by the elevator. Yeah, floor 3, right by the elevator.
Oh.
All right. We're gonna dive into a deeper look at parsing. So historically, I haven't really had time to go into each one of these steps at a deeper level. And what will map closest to the difficulty that we've talked about in this class is the parsing step. And there's also a lot more to learn about the parsing step. It is quite deep and quite involved, but it represents the most interesting deep dive that we can go into given the time that we have left. Since we have a little bit more time than I have historically, maybe we can do something else, but I at least want to make that deep dive so that we understand a bit deeper. How do we parse efficiently? Because we can parse anything with CYK, but with cubic time complexity, that's not ideal if we can do better. So we've talked about explored parsing at a basic level. So we've seen CYK, we saw that it was cubic. Well, first we saw that there was exhaustive search, and we saw that if we really brute forced this, it was exponential complexity. And to do exhaustive search or brute force, we just started with the start non-terminal, and we started to say, all right, what's every rule that we could apply? What's every rule we could apply to that? What's every rule that we could apply to that? And that eventually generated every string that we could in the language. But that was exponential in complexity, because at every stage we were applying some number of productions to every set of productions that we'd applied before. So we would have, there were 3 legal productions to apply. On one step, we'd have 3, on 2 steps, we'd have 9, 3 steps, we'd have 27, that's exponential scaling. However, if there are multiple productions for a particular left-hand non-terminal, then that creates an additional branching factor for that, so we modify the base of that exponential. So the complexity was very much exponential, which is bad. So we're gonna start diving into LL parsing. Looked at it briefly before, and we're gonna realize just how much more complicated it is than we think it is. But by the end of this, I'm hoping that it really makes sense, because it does. So a couple of different parsing approaches that we might take to a particular program. You could start with this concept called top-down. It's very similar to other top-down algorithms that you might have seen. We start with the start non-terminal, and we're going to try to derive the string that we're trying to match via an intelligent search in the list of productions. So exhaustive search is a top-down approach. We just don't use any intelligence. We do a full search of the search space. LL is going to be a top-down approach where we're going to be utilizing as much information as we can before we start applying those productions. We'll do a minimal search, or we're going to end up using a couple of concepts like which productions that we apply could produce the next letter in the string that we are looking for. If we can do that kind of pre-processing on the grammar, then we can start to get a sense of which productions could we possibly apply for this. We could also think of a bottom-up approach. So we start with the string, and then we start trying to replace groups of characters in the string with the associated non-terminals by going right to left, replacing the right-hand side of a production with the non-terminal left-hand side. And eventually the goal is to derive the start non-terminal from all of that. Replace the string eventually via some number of inverse productions with the start non-terminal. We're going to talk about LR parsing as the last thing that we cover, and LR is a bottom-up approach. LL is, they're basically equally efficient. LL is simpler, but more grammars are LR than LL. So LR actually has a wider net that we can cast, but it is more complicated. So we're going to start by talking about LL. So top-down parse, you can start with a leftmost derivation and parse tree from that. So what would that look like? Well, we could start with something like S goes to A capital B, C. A goes to A capital A. And you can continue this process throughout until you derive something like A, B, B, C, B, C. And that is a string in this language. And we know that we went top down as we did this. If we were trying to map exactly to that string by, you kind of have to either guess and check or use some kind of logic to try to determine which productions are going to map eventually to the string that we're looking to produce. But we start with that start non-terminal, and we make some number of production expansions until we either find the string or can somehow prove that this grammar can't generate that string. So that's top down. Start with the start non-terminal, try to derive the string. Bottom up, on the other hand, same grammar and same rightmost derivation. If we can try to construct a bottom up parse, it's useful to visualize this. If you start with just the set of productions that we used in the left to right, now you can start to see that, all right, we know that that B can backtrack. This B can backtrack to be a capital A, which can backtrack now to this AB can, let's see, it's this AA. This AA backtracks to be this A. And then this C becomes a B, and then this becomes the AABC. So we're kind of going backwards as we're applying right to left, right to left, right to left as we generate that. The arrows for this are kind of reversed in that you start by looking at not the entire string necessarily, but just the local portion of the string that you need to be able to make those backtracks. continuing to do that process until you can derive the start non-terminal from the string. So this is kind of a top-down, the full view of the process that we went to, as we found that we can make that, but we couldn't do this until we had done that. So it creates kind of either scheduling, or it's not really scheduling, it's you have different decisions about what you can do at any particular point in time. And the question is now, can we just derive the start non-terminal via some sequence of these right to left production applications? Questions on top down versus bottom up? I'd be curious to say, which one of these do you feel like is more intuitive to you?
On the surface, bottom up seems a lot more intuitive because we're starting from strengths and we try to work our way back towards the beginning.
Mm-hmm.
Versus, but I think programmatically top down is a lot easier to code.
Interesting. I'll be curious what people have to say after we're done with it. Anyone else agree or disagree with Shane?
Bottom, like figuring out what productions would create the string, starting at the string would be.
Yeah, maybe it makes more intuitive sense.
Like when programming it, that's. Cause that program kind of like going through text before with
Right.
like a state. And usually I do my state management based off of what character I've just read, and I
Mhm.
figure out what I would then expect after that.
Yeah, I think most people are gonna change their mind by the time we look at LL and LR. When we look at how this is actually done in practice, it's significantly simpler with the speed ups that we can find and the information that we can gather via analyzing the string ahead of time. Top down actually is significantly easier. However, bottom up is more complete in that there are more grammars where it is possible to utilize a more complicated speed up to make that work.
That was kind of my intuitions.
Yeah,
It's usually stuff that's easy to understand on the surface, and then you have to put that into a program. Suddenly, it's a lot more difficult because the computer doesn't process it the same way. Versus a human, I could say, oh, from there I could go back.
right. So what we're gonna find if we're trying to do this efficiently is that we need to do some pre-processing. We need to look at the grammar and look at the string and be able to come up with some information that we will eventually use when we need to make decisions. Because we know that if we just continuously apply a branching factor without making any kind of decision on this, then the issue that we run into is that the search space is too large. So we need to reduce that search space by intelligently looking at when are we going to hit a dead end. If we know that steps in advance, then we know which productions to not apply when we are doing this. So the first one of these is unironically called the first function. So let's first define what this means. There are multiple applicable rules in a top-down or bottom-up parse. So that means that just there's a branching factor in this tree. There are multiple possible productions that we could choose if we have something like S arrow ASB or A capital A. Something like this. We would have a choice. And if we're trying to map this string to this grammar, we don't know which production to apply. We need some way of choosing which one of those is going to work and knowing which one of those is going to work. So two functions that are used in both LL and LR parsing. The first function, which is all capitalized for the most part, even though for the most part, I will be using it capitalized most frequently. But given that we have our grammar, the output to this is just the terminals that could become the first character from a string that is derived from this production. So if we have something like S arrow lowercase a capital S lowercase b, we know that if the next character that we're going to read in the string is B, we should not apply that rule, because the first terminal that becomes part of that is a lowercase a. There's no reason to even look at that, it's gonna fail immediately. But what if we have something like S arrow capital A lowercase a? And that capital A is capital B lowercase c. We might need to use some kind of recursive logic to dig into the definitions of non-terminal, 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 to try to figure out what are the set of possible first symbols that we could apply if we used this production. But we can also figure that out at the pre-processing step. We don't need an associated string, and it's based on the grammar, not based on the string that you pass it. So a first function will be unique to a grammar, not to a grammar string pair. Which means just with the grammar, we can build out a table of this first function for every production. First thing we need to define, the first of a terminal is just the set that is itself. So first of lowercase a is the set that contains lowercase a. This makes sense. If you have a production where the right-hand side is a single terminal, the first character of a derived string from that must just be that terminal. Capital A arrow lowercase a. There's no way to start a string, given that you're at that capital A, that begins with anything but a lowercase a. The first of a non-terminal is going to be an iterative process. Begin with, initialize it to be the empty set, and we're going to now explore this grammar iteratively, or recursively, and as we explore it, we're going to be adding symbols to this set. So the first of every non-terminal, which is going to be defined at some point in the grammar, assuming that it's reachable. The first of a particular left-hand side is the union of the first of each production in the right-hand side. So if we have something like S arrow capital A or B, then we would say something like first of S is going to be defined to be the first of capital A, since that's what starts this production, union first of the lowercase b, because that's what starts this production. And since we already defined that the first of a terminal by itself is itself, we could then just replace this with the set that contains B. And then we have to do a search, a recursive search, to now define first of capital A. Once we have that set, we can union this B with the answer to that. So we can't answer this yet because it depends on first of A. I think what's really important here is just that initial definition of what are the possible terminals that could start a string if we're at that non-terminal. The first of an entire production is the first symbol in the right-hand side of that production. So that's exactly what I just said. If we had the right-hand side being capital A, lowercase a, we don't care about that lowercase a. It can't possibly start that unless that A can derive lambda. But we'll talk about that momentarily. That's where this becomes a little bit difficult, because non-terminals can sometimes just derive lambda. And then the second symbol actually has relevance. If both the first and second symbols can derive lambda, the third symbol has relevance. So the little bit small here, let's quickly zoom in on this process. This is kind of the algorithm for generating, just a little closer. There we go. Not that much. So this is kind of the book's algorithmic process for every symbol in the list of terminals. We define the first of that terminal to be the set, including itself. We define the first of lambda to just be the set that contains lambda. Wasn't mentioned on the slide, but that kind of makes sense. If we can't derive anything from there, then we can't. For every non-terminal in our set of non-terminals, B is the set of non-terminals, T is the set of terminals, variables and terminals is what the book is going for there. for every non-terminal in our set of non-terminals, initialize the first of that non-terminal to be empty, and then iterate or recurse until there are no more terminals or lambda can be added to any first set for every production that utilizes that non-terminal. So in this case, we're using A as an example. For every production where A is the left-hand side of that, then we're going to define the union. First of A is still the first of A, union the first of whatever character that happens to be. This W can either be a terminal or a non-terminal. Last step, for every possible production now that we're breaking down into a set of symbols. So X1 is the first character in the right-hand side of a production. So W is just that string. We're going to say first of W is now the first character in that, minus lambda. For every other character, if the prior character can derive lambda, then we need to look at the first of the next symbol. You can imagine this as something like, I'm going to be potentially, I have an idea for this, but to do this, it might be potentially offensive. So if you love the French language, I'm sorry.
Just because I have an
Imagine the first character in a French word that you actually pronounce. There could be 1 or 5 silent letters at the beginning of a French word. Just because I love shitting on French. It's fun to do.
It's because their spelling is garbage. Like, why is Vo B-A-B-E-A-U-X? Why?
I think it should be A-U-X-B and just make the first letters.
Oh.
Imagine if that were the case. You can have a bunch of silent letters before you start pronouncing the word. If the first letter is silent, we have to look at what the second letter is. If the first letter isn't silent, we don't care what the second letter is. It's very similar for this. If the first symbol in this production can derive lambda, then the first terminal that could appear could be the second symbol. If that can derive lambda, it could be the third symbol. We have to keep going as long as this could derive something that is not pronounced, something that is not a terminal in the string. So I think it's very similar to that concept of choose a language with a lot of unpronounced letters. What is the first pronounced letter? Keep looking through silent letters until you reach the first letter in that word that is pronounced. Keep looking through symbols in the string until you find one that can derive, the first thing that it is guaranteed to derive is a terminal. If a non-terminal can derive lambda, then it's possible that the next symbol in that is the first symbol that can derive a terminal. Then as we continue to do this, just add this iteratively into this set of first for this symbol. Whatever branching we can do, whatever we can use to go search through this space, I think it makes more sense with an example. So I'm going to backtrack here and just go into an example. So first of S for this grammar, how would we go figure this out? Let's actually write out what we would do. And then I'll show you the book's way of handling this. So first of S, we can define it to be the first of every starting character for this, but we have to look for whether it can derive lambda. Luckily, there's no lambda anywhere in this grammar, so we're not going to worry about it. First of S is defined to be first of A, this first symbol of this, union first of capital A. So we can instantiate first of A as the set that contains itself. First of A, on the other hand, we have to define that because it's not immediately apparent from, we don't have a definition for it. So let's define first of A is going to be first of B, union first of C. We know this is the set that contains B, we know this is the set that contains C. Once we have this definition for first of A, we can substitute. So this is a union to that. So now we can say that this is the set that contains B and C. Union this, and the final answer is A, B, and C. And this makes sense because you can imagine paths through this grammar where the very first symbol is A or B or C. For instance, we could generate S arrow A arrow C, and that generates a C as the first character in this associated string. We could go S arrow A arrow B capital A C arrow B C C, and we have a string that starts with a B. We could go S arrow A capital S B arrow A capital A B arrow A C B, and now we have a string that starts with an A. So really, this is all that the first function is trying to tell us in this case is what are all of the possible terminals that could begin some string from this particular non-terminal, if that's where we are in the grammar. And we do that by kind of recursively constructing this. Now, the way the book does this is a little bit more confusing, but it's also more algorithmically sound. If you were going to go implement this, then you would want to do something more like this. So note that it's utilizing the entire production here. And that's because in general, you can combine a couple of rules. If this started out being a non-terminal that could derive lambda, you would want to be able to check the next character in this production. It's only through my looking at this and saying, well, if it starts with a terminal, why look at the rest of it? Because there's no way that that terminal can derive lambda. So it's just a little bit easier to code, fewer cases to consider. But intuitively, if I'm constructing this, if it starts with a terminal, I don't need to write it out quite this rigorously. You'll get to the same answer. Questions on this? Basically, this just combines now into, we now have a definition for first of A. So first of S just becomes the empty set union A, union BC, gives us the ABC that I derived.
Not that bad.
It's not that bad.
To the last slide real quick, I was wanting to finish writing out the algorithm. Thanks.
Yeah. Where do we want? First half or second half?
Or first half, sorry.
Anyone else have any clarifications I can make while we're taking notes? This algorithm will end up being pretty important because this algorithm is actually your second project. Coming up with it and then applying it in an LL grammar. So the first is just coming up with, so it's not just this. This is just the first function. You'll need first and follow, which we'll talk about next, and then LL. LL is mainly just lookups of the first table and a follow table to be able to construct a table that allows us to determine which production to apply. And if we can guarantee a particular production within some number of lookups, then we end up with a linear time algorithm for parsing a grammar. All right, here's the second half, for those of you who were right in the second half. Yeah, these absolutely will be posted. So you don't feel like you need to take absolutely perfect notes unless that is something that you want to do. That is the exact process that was used to derive the example first function on the next slide. How do we feel about the first function? Feel like does it make intuitive sense at this point?
Feel like program.
That's where I would hope people would be in an ideal world. Sometimes we live in that ideal world, sometimes we don't. All right, let's dive into another example. Here's an even simpler grammar, but how do we calculate first of S in this grammar? Intuitively looking at this, can this grammar start with a B? Can a string in this language start with a B?
Yes.
Can it start with an A?
No.
All right, make sure as you go through this, that the process you go through aligns with this idea that we cannot start with an A. This should only derive B.
Left linear, so we can only produce.
Yeah,
more.
so if you're coding this, this is an example of very simple grammar where you can make sure that your program does not go into an infinite recursion. If you're going to define first of S in terms of first of S, which needs to be evaluated, which gives you first of S, which needs to be evaluated, which gives you first of S. It's a very easy grammar to check for that infinite recursion, because you want to check, have I already defined first of S? If that's the case, then terminate. That becomes your one of your base cases. So we get something that looks like this. We know we define it as of itself, which starts out empty, union it with the first of each production. We know that first of B gives us B, but we start defining this recursively, defining first of S in terms of first of S. As soon as you do that, you can stop. However, we need some examples with lambda in them, because as soon as we can start with those French words with a silent first letter, our life becomes a little bit more complicated. So we define first of lambda to be lambda. If we have the ability to derive lambda in the first of some non-terminal, we have to consider the production that comes immediately after it and continue doing that recursively for any of those that could derive lambda. So let's take a look at what that looks like. We want the entire first function for every non-terminal in this grammar. So start with each of them being empty. And then see if you can fill them out. Which one's gonna be easiest? Looking at the grammar. A is gonna be pretty easy. B is gonna be pretty easy. S is not gonna be quite that easy. Think we got there? First of A and first of B are pretty straightforward. First of A is itself, which is empty. Union each production, first of each production, first of anything that starts with a terminal is gonna derive itself. So we get empty union C, union D, giving us the set C and D. First of B, itself to be empty. First of each production, the first one starts with a terminal, so it's just that terminal, B. And first of lambda is defined to be the set that contains lambda, so we get the set that contains B and lambda. We now have everything we need to answer first of S. And if you're writing this programmatically, if you start with first of S and find that it depends on first of capital B, then you can just recursively calculate first of capital B first before you move back and try to calculate first of S. But we find that when we do that, it's a little tricky because first of capital B, we've now defined to be B and lambda, and we can now state that because it contains lambda, we're gonna add this B to the set that is first of S. So let's actually just write this out. It's gonna start with itself, the empty set. I don't love writing that all out on the
It
board.
also seems not even worthwhile to include the set within itself, because whenever you derive it, it automatically goes to an empty set, which you don't use ever, so.
Yeah,
On my notes, I made the executive call to alias F to first, because writing
Yes.
first is a
Well,
lot of writing.
One RST.
keep in mind that the next thing we're gonna do is follow, which also starts with an F. So as long as you have an FI or an FO or an F and an FO or
Yeah,
what's coming next will have that same alias and you keep it to a single character.
I define it per page.
There we go.
One RST.
First. Fit, fur, fist.
I like this.
What can we derive in order? Anyway, since this, we're gonna add now the first of this, which is just the set containing A. So now we've dealt with that production. This production, we need first of B. So union first of capital B, which I'm actually gonna utilize the entire one this time. First of B, capital A, D, because we're actually gonna need to refer to that. So this is going to include everything from here, except instead of including the lambda, because it actually can't include lambda unless we get all the way to the end. So we're not gonna include the lambda, but we're gonna use it as a branching point to say now we also need to consider the second character of this. So this is going to partially be B, but we now have to consider now this union of this first of capital A, because if the B goes to lambda, then whatever A could become as its first terminal also could be what is first derived here. So we now union that with everything here, giving us the C and the D. Want to convince yourself of this, come up with a string that, starting with the start non-terminal, starts with each one of these characters. You wouldn't get C and D unless you found this lambda and used it as a way of saying, now look at the next symbol. So you can generate something like S arrow B A D. This B goes to lambda, so we just get AD, and this A now becomes DD, maybe. And now we have a string that starts with a D. A little bit harder when we include a lambda, but the main thing algorithmically that I like to think of is if we find this lambda in one of these, then include everything, still union it, but now add an extra instruction at a next step that says, look at the next character of this and add everything from that. If that can go to lambda, continue that process. And if you ever get to the end of this structure, you will union this with lambda. If there is no next character to go to, then you should union that with lambda because everything can derive lambda. How are we doing? That make sense? All right. There's the whole structure. I've kind of been doing this next thing along the side of this, which is just verifying that the first function that you have derived is correct. How could you do that? Work in the opposite direction. For each element of first of S, show some derivation where that becomes the first symbol in that string derived from there. So we can utilize this process to now give an example string where starting with S, we can derive some string that starts with that terminal. And also is a full string. So I don't really like the second one there that shows S arrow capital B capital AD and you stop showing B coming first. That's kind of a problem because that's not a terminal, that's not a full string of a derivation. It could be that one of those is an infinite recursion. So this is relying on the fact that we have looked for useless productions before doing this. So we talked a couple of weeks ago about the concept of a useless production. You can stop at this stage if you have already found all of those useless productions. But if there are potential useless productions in your grammar, then that's not necessarily a complete proof that you can generate a string that starts with that character. So you can continue to do that for every non-terminal and left-hand side in the grammar. Very good natural stopping point because we're about to talk about follow, which is a little bit more complicated than first. So we will come back on Monday, recap first, and get back into a follow function. If we have first and follow, we can then look into the LL algorithm that can parse a context-free grammar in linear time, assuming that the grammar is in a particular form. Go team. I don't usually technically have office hours on Friday, but since we have a department meeting, I will be around until 2:30. So feel free to come keep me from dying boredom. Ask me questions, look at magic cards. I don't care what you do. Just keep me from dying of boredom. Fest is tomorrow, yes, if you haven't. If you're signed up for that, I will be here all day tomorrow. Cheering you on.